Hey folks, how's it going? Mr. Murray coming to you with a video on piecewise defined functions. So this is going to be an introduction video to the next unit that we're going to be covering this year. And I hope this video gives you a sense of not only what is a piecewise defined function, but the various skills that you all need to be able to execute related to these types of functions. After we learn about what piecewise defined functions are, the next component of this unit will be to talk about a special example of a piecewise function called a absolute value function. So let's start with, what is a piecewise defined function? Well, as its name suggests, a piecewise defined function is a function that's defined by pieces of other functions. If we take a look at this graph right here, this is a graph of a piecewise defined function. And actually, there's three different pieces, right? We have this curve here. This is piece 1. We have this little flat line here, piece 2. And we have this line, piece 3. Now, we would probably assume that there are arrows on the end, so I'll go ahead and put those in. But in any case, these are the three pieces. So one piece, there's a little bit of x squared. Okay, there's a little bit of the graph. This would be 3, okay, because this is constant, and the y value along this piece is always 3. And then finally, there's another piece, and this one's a tricky one, but this one, believe it or not, is called x. Whatever the y is, it's always going to be equal to the x. And so we don't always use x squared, right? So as we're going to learn, x squared only applies when x is less than or equal to 1. Okay, you can see here, if I look up and down, this is 1 on the x-axis. So as long as x is less than or equal to 1, we're going to be using the rule x squared. When x is greater than 1, but less than or equal to 2, we're going to use the graph of 3. And finally, when x is greater than or equal to 2, we're going to use the rule x. Okay? So this is an example of a piecewise defined function right here. And again, you can see it's made up of 3 different graphs that we use depending on what the x value is. So again, when x is less than or equal to 1, we use one relationship to describe the outputs of the function. When x is between two values, that is namely 1 and 2, we're going to use a second rule. And when x is greater than or equal to 2, we're going to use a third rule. Technically, there are no limit to the number of pieces you can have in a function. You're supposed to use, usually 2 or more, because if there's only one piece, then it's not really piecewise, it's just one type of function. But that's the idea, folks. We're going to be talking about in this video what these things are and what you can do with them. So there's 3 main skills we need to focus on. We need to focus on evaluating if I give you a formula or a graph. That is, if I tell you what x is, what is y? Or f of x. They have the same meaning, essentially. Graphing given a formula. So if I give you a formula, can you create its corresponding graph? And as I just did earlier, a moment ago, writing a formula given a graph. So if I give you a graph of a function, what is the formula that goes along with it? So these are 3 really, really important skills that we need to work with when it comes to piecewise functions. Okay, so in this video, we're going to be seeing each of these skills one at a time, and then there's going to be opportunities for you to practice not only the individual skills, but the skills together. So the first skill is to evaluate a piecewise function. So again, evaluate means find the value. If you look inside the word evaluate, you see the word value. So what I'm saying is, if I give you the x, can you tell me the y or f of x? So here's how we do it. We first look at the input or x value. That is, we look at what value are we being asked to plug in. Then what we're going to do is we're going to look at the inequalities, and that's going to tell us what rule we're going to plug into. Because remember, a piecewise function will have multiple rules, and we only want to ever plug into one. And then, based on the rule that we're supposed to plug into, that will tell us the output. So remember, you should only ever plug in to one expression at any given x value. Because if it's a function, an input must have one output. That's like the central definition of a function. A rule that gives every input exactly one output. So let's take a look at some examples. Here I have three rules: f of x, g of x, and h of x. F of x says that if x is less than or equal to 0, the output will be 3, always. And if x is greater than 0, the output will be 2. G says if x is less than or equal to 3, use the rule x plus 5 to determine the output. And if x is greater than 3, use the rule 2x minus 1 to determine the output. Finally, h of x says if x is less than or equal to negative 2, use the rule 1/2 x minus 4 to determine the output. And if x is greater than negative 2, use the rule 3 minus 2x to determine the output. So let's see if we can figure some stuff out here. So first we're going to do f of 2. So we're going to ask ourselves, let's look at here. X is equal to 2. See how 2 is where x is supposed to be? So we're saying x is 2. So is 2 less than or equal to 0 or greater than 0? 2 is greater than 0. So we're going to use the second rule, which is 2. Here in this first example, it doesn't matter what x is. The y or f of x is always the same value. It's either going to be 3 or 2. And we'll take a look at what that looks like when we get to the graphing. All right, next, we'll go over actually to f of negative 4. So negative 4 less than or equal to 0 or greater than 0? Negative 4 is less than 0, so we're going to use the first rule. And that says it's 3. All right, next, 0. So this is tricky. Is 0 less than or equal to 0, or is it greater than 0? Well, because of the or equal to, we're going to use the top rule, which is 3. And finally, f of 1/2 is a half less than or equal to 0 or greater than 0. It is greater than 0, so we're going to use the second rule. All right, now we're going to look at some examples where we're actually going to need to plug in. So let's do g of 7. So we come to the second rule. G is 7 less than or equal to 3 or greater than 3? 7 is greater than 3. So we take 2, we're going to plug into the second rule. So 2 times 7 minus 1. We plug into the x on the bottom because the rule says to do that if x is greater than 3, which it is because x is 7. So 2 times 7 is 14, minus 1 is 13. Okay, how about 0? Is 0 less than or equal to 3 or greater than 3? It's less than or equal to 3. So now I'm going to plug into the top rule because we're told to use the rule x plus 5 when x is less than or equal to 3. And we see here 0 is the x, and that's less than or equal to 3. So my rule, I do 0 plus 5, which is 5. And I'm just going to circle these so these don't get too confusing. All right, negative 1. Is it greater than 3 or less than or equal to 3? It is less than or equal to 3, so I'm going to plug in up top. Negative 1 plus 5 is 4. And now 3, so you can see we have these issues when we're on the cusps. 0 is an example. 3 is another example. So 3 is less than or equal to 3, so we are again going to plug into the top rule and do 3 plus 5, which is 8. All right, now we're going to look at the last rule, and let's take a look. So here, h of negative 4. Is negative 4 less than or equal to 2? Negative 2, that is, or greater than negative 2? Here it is, less than negative 2, so we're going to plug in to the x on top. And notice again, you only ever plug into one x value because every input, as you see here, can only have one output because this is a function. So a half times -4, that's the x value, minus 4. Half of -4 is -2, which when I subtract 4, I get -6. All right, h of -2. Again, we're on the cusp. -2 is equal to -2, though. So that means I'm going to use the top rule. So see, again, I'm only plugging into the x in the top rule. A half of -2 is -1, which when I take 4 away from it gives me -5. Here, -1 is greater than -2. So now I'm going to plug into the bottom rule because my function says if x is greater than -2, plug into 3 minus 2x. So I'm doing 3 times 2 times -1. This cancels and I get 3 plus 2, which is 5. And 6 is also greater than -2. So I plug in here 3 minus 12, which is -9. Okay, so again, this is the idea behind how to plug in. You look at the rule, you look at the x value you're supposed to plug in, you determine which of the inequalities is true, and only one of them should be, and then you plug in to whatever rule corresponds to that inequality. So as you see here, if the top rule was true for x, we plug in for x in the top. If the second rule is true, we plug in for x on the bottom. So it's just about looking at the inequalities, figuring out which is true, going over to the left, plugging in for the x. Please make sure you understand how to do this, and then in a couple seconds, we'll move on to the next type of skill. All right, next skill, graphing a piecewise function. So here's how graphing works. What we're going to do is we're basically going to be graphing the entire piece. We're going to forget that the inequality is even there. Then what we're going to do is we're going to use our eraser to erase the part that should not be on the graph based on the formula. Okay, that seems like a lot, but the first thing I want to notice is use pencil. Okay, the other thing I want to note is notice that the inequalities say x. That means that the x, not the y, is going to be our guide. So there's two main mistakes people make. Okay, the first is erasing the wrong side, and the second is erasing based on y instead of on x. And when I say y, it's f of x or y, okay? So these are the two big mistakes that people make, okay? And I'm trying to tell you about this before I jump in because I want you to avoid making these mistakes, okay? So this is what I'm going to do. I'm going to look at this graph. Our graph is f of x is equal to. So if x is less than or equal to 2, we're going to use -2x minus 1. And if x is greater than 2, we're going to use -x plus 4. So once you get the hang of it, you actually don't have to use the erasing strategy. If you can look at it and know where the graph starts and stops, that's great. But using the eraser is the most consistent technique that is always going to work, especially in scenarios where where you have like slope-intercept form, but the intercept is not part of the graph that you're supposed to keep. And you'll see what I mean in a minute. So first, I'm going to go to -2x minus 1. Okay, so -2x minus 1 has a slope of -2 and an intercept of -1. So I'm going to go ahead and plot that. Okay, there's my line. And then what I'm going to do, put my arrow, and I'm going to connect. Okay, and because I'm doing this on a tablet, I'm going to probably need a couple of attempts. Okay, there we go. So there's -2x minus 1. And you'll be able to do a better job because you're going to be using a pencil and maybe a ruler or some kind of, you can use your will not dot fail card for a nice straight edge. All right. Now, what part of the graph should be on the final answer. So I want to only keep the part where x is less than -2. So what I do not want is where x is greater than -2. So here, sorry, that is +2, where x is less than +2. That's what I want to keep. So I do not want where x is more than +2. So here, x is more than +2. Right here, x is 3, 4, 5, 6. So I'm going to erase until I get to where x is equal to +2. And then I didn't mention this, but what I'm going to do is I'm going to make this dot nice and extra dark. And the reason I'm going to do that is because this inequality is greater than or equal to. So greater than or equal to, or I guess in this case, x is less than or equal to. But in either case, if there's an or equal to in the inequality, you're going to use a filled in dot. Okay, and then as you see when I do the next one, because this is not or equal to, I'm going to use an open dot. So let's do the next part. The next part is at -x plus 4, okay, because we're done with this one. So I go 4, and this graph is going down by -1. So here's where it gets confusing, right? So now I'm going to graph the whole thing out. Nice, put that arrow on. Put that arrow on. And I only want to keep the part where y, or that is where x is more than 2. So I'm going to erase everywhere where the x is less than 2. Okay, x is less than 2 here. Let me just go ahead and tighten that up because I accidentally erased some of it. Okay, erase, 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 erase. Okay, and what I'm going to do, I'm going to leave an open dot where x is equal to 2 because this is not an or equal inequality. X is strictly more than 2. Can't be equal. It's got to be more than. So one thing you're going to notice that's going to tell me that this graph is correct. You can see here I'm making a little line. And this line is to do what we call the vertical line test. So if I run a line from left to right, that line can only touch the graph at one point. Okay, that's how you know it's a function. This line tells me how many outputs each input has. So here we have one output, one output, one output. We're all good. Okay, here it's kind of weird, but this is only one output because the open dot doesn't count, but the closed dot does. So this only has one output, and then one output, all one output. So this actually does pass the vertical line test. So this one is going to be a function. So that's one way to know if you've graphed it incorrectly or you've erased the wrong side. If you run an up and down line over the graph and you can see it overlaps, right? It crosses two of the pieces at the same time. You did not do the graph correctly. So go back, and most likely the reason that you got to fix is that the wrong side was erased. That's most likely what the reason was that didn't work. All right, so please make sure you understand what I did here, and then what I'm going to go ahead and do is move on to the next skill. All right, before I do, notice again I said sometimes two pieces meet up. That is okay. So what I'm saying is sometimes, as we're gonna see maybe in some practice problems, when we get to the crossover point, which here would be 2, because the x is less than or equal to 2, x is greater than 2, sometimes the y values are the same. And so what the closed dot does is it actually fills in the open dot. That's perfectly fine. It just sometimes they don't meet up and sometimes they do. It just depends on the particular formula you have. All right, last piece is that we got to learn about is writing a piecewise function. So for each piece, you're going to pretend like it's going to go on forever in both directions, as if it never got cut off at all. And then you're going to use the starting and ending points to write the inequalities. Note that not all points are going to start and end. As you can see here, we actually have 3 pieces, and you always want to do it from left to right. So 1, 2, 3. Now 1 doesn't have it right. It has an ending point, but it doesn't have a starting point. 2 has a starting point and an ending point. It's what we call a line segment. And 3 has a starting point, but no ending point. So 1 and 3 are what we would call rays, because a ray has a starting point, but no ending point. And 2, again, would be a line segment. So here's what we do. First, we're going to set up our f of x equals. We're going to write our squiggly bracket here, and we're going to go one piece at a time. So what we're going to do is we're going to stretch this, and we're going to pretend like this graph, even though it doesn't, went on forever. If it did, what would its formula be? So we can see this one has a rise of 1 and a run of 1. That is a slope of 1. And if it kept going, it would intercept the y-axis at 2. So this is the graph of y equals x plus 2. Where does the graph start and end? So it has no end, but where we notice that this is the part of the x-axis where x is less than 1. And because this is a closed dot on the end, we write x is less than or equal to 1. All right, second piece we're not going to stretch because we can see the slope and the intercept. It actually touches the y-axis. So here again, the slope is 1. The intercept is 3. And this piece, and I'm sorry, this should not be 1. This should be negative 1. So again, you can see that mistake people make. The big mistake is that people, I'll write the mistake, is using y's or f of x's instead of x's for the inequalities. Using y's or f of x's instead of x's for the inequalities. The number one mistake people make. So this should be negative 1 because x less than or equal to negative 1. Here, this piece is going to be when x is between negative 1 and 1, because again, you look on the x-axis, negative 1 and 1. Okay, and then the last piece, let's stretch this out. I mean, if you can see where it's going, that's great, but you're welcome to write all over the graph in one of these kinds of problems so you can see what's actually going on. And this is the graph. Remember, we're going from left to right, x plus 1. Okay, and that's when x is greater than or equal to 1. So again, one of the big reasons to extend the line is that another mistake that people make is they get their slopes mixed up. So it's hard for them to tell what's going on with the slope, but remember the slope, you're always going from left to right. So really extend that line out if needed. Right, so this is our function. Okay, here's our rule. F of x is equal to x plus 2 when x is less than or equal to negative 1, x plus 3 when x is between negative 1 and 1, and x plus 1 when x is greater than or equal to 1. And again, notice the connection between the dots and the inequalities. All right, folks, hopefully this made sense. Please go back and rewind if needed. Then in a moment, we're going to move on for a couple of problems for you to try. All right, so I'm going to have actually 2 problems for you to try. In this problem, what we're going to do is we're going to practice graphing and evaluating. So you need to graph the function, and then you need to plug in 3, -4, and -2 and tell me what you get. Actually, you have the freedom to do either one. You can evaluate first or you can graph first, as long as you do both of the tasks. So please take a moment, pause the video, attempt this problem, then when you're ready, unpause, and you can see what I got. All right, so I'm going to start by doing the graphing. So I'm going to start with the first piece. Now, usually a piecewise function goes in order of the x values from least to greatest. So the top piece is going to be the piece that you're going to want to graph first. This one has an intercept of 5 and a slope of 1. It's really, really important at this point in the game, folks, that you guys know how to graph a linear function in y equals mx plus b form. I do kind of have to assume that you know how to do that pretty fluently, and if not, that's perfectly fine. But then we need to talk after school or during some kind of extra help period about how we're going to get you up to date on that. All right, so this is the whole graph, but wait a minute, we don't want the whole graph. We only want the part when x is less than -2. So this is -2 on the x-axis. We only want to have what's remaining be the piece when x is less than -2. So we're going to erase everywhere where x is more than -2, because that should not be on the graph, because that is not where this inequality is true. So we get to -2, we put an open dot on the graph because it is not or equal to, so it's an open dot, just like a dashed line for two variable inequalities. Remember how we use the dashed line when it's not equal? Very similar idea. All right, next piece, -2x minus 1. Boom. Now notice you're going to see it's going to meet up. Okay? So that's a common place where people get confused, and that's okay. So we're going to, again, graph it, connect it, lines on both sides. Then we only want the part where x is greater than or equal to 2, -2 that is. So we're going to erase where x is more than -2. We get to -2, and because it's so equal, you can see we fill in that open dot. And that's what's going to happen. When in this kind of scenario, the open dot is going to fill in the closed dot. That's perfectly fine. You know, if you're doing this on a test or quiz, it's going to be hard to necessarily know in the end result that you filled it in, but that's okay. This is what the graph happens to look like. All right, let's evaluate. So f of 3, we can see on the graph that when x is 3, y is 1, 2, 3, 4, 5, 6, -7 if we kept this graph going. What if we plug into the function? So when x is 3, is 3 less than -2? No. Is it greater than or equal to -2? Yes. So we plug into the x on the bottom, because that's the rule you use when x is more than or equal to -2. So -2 times 3 is -6. -6 minus 1 is -7. All right, next rule. So we have -4. We can see 1, 2, 3, 4. It appears it is equal to 1. Let's see what happens when we plug it in. So is x less than -2? In this case, it is. So we plug into the top rule, -4 plus 5, which gives us 1. So you can see we can use it based on the graph. What is y when you know the x, or using the formula. Finally, -2, we can see -2 goes with 3. Let's verify. Is -2 less than -2? No. Is -2 greater than or equal to -2? Yes. Now in this case, it actually wouldn't matter. You'd get the same answer either way, but obviously it's the proper thing to do is to plug in based on whichever inequality is true. So here you get -2 times -2 is +4, which when you minus 1 gives you 3. So please make sure you understand what I did there. Not easy stuff. Then when you're ready, go ahead and we'll move on to the last U-try problem. All right, folks, last U-try, what I want you to do is I want you to write the rules based on these graphs here. I'll tell you in the first one, you should have 2 pieces. In the second one, you should have 2 pieces. And I'm going to actually let you figure out what you should have in 3 pieces in the third one. For the second and the third, that is, let me number them. For 1, 2, and 3. For the second and the third, you and I may disagree on the inequalities that are used in the piecewise function. That's fine as long as your piecewise function makes sense. Okay, that is as long as one of the inequalities is or equal to and the next inequality is not, so that you're only ever going to plug into one x value at a time. I'll talk about that more in the solutions, but for now, please pause the video, try to write the 3 rules, then when you're ready, unpause, and we can see what I got. All right, so let's start with the first rule. F of x equals, let's open up my inequality, or my bracket here. So my first rule, I'm going to pretend like this goes on forever, so I'm going to just stretch it up till it hits the y-axis. So I've got a slope of 1, and then intercept of 1, 2, 3, 4, 5. So it's x plus 5. Now I'm going to go back and look. So one strategy that I think a lot of people do is they make an up and down arrow through that like turning over point. So that is when x is -2. And because this is an open dot, we're going to write x is less than -2. What about the third rule? Well, this one's a flat line. This is a value of -2. It's always -2. There's no slope because it's a flat line. And this one is x is greater than or equal to -2. All right, next one, I'm going to call this one G. What you call it doesn't really matter unless I tell you what to use. So this could have two possible answers. The first one we can see is the first one is the graph of y equals x when x is less than 0. This is the turnover point at 0. And then you appear to have 2x when x is greater than or equal to 0. Now, if you had said the top one is x is less than or equal to 0, that's fine as long as on the bottom one you say x is greater than 0. So basically, as long as this or equal sign is only on one or the other, it doesn't matter which one you put it on because the graph itself doesn't make it clear where it's supposed to go. But as you can see here, if x is equal to 0, it's clear that you're only supposed to plug into the second rule. If I put or equals on both of them, then you create an issue because then you're plugging in to two rules, that is the top and the bottom, and you only plug into one x because an input should only have one output. Here they do happen to be the same, but that again is not always the case. All right, final one is h of x. This one turns out to have 1, 2, 3 pieces. So, first piece. This shows you why you really want to extend the graph out because it doesn't actually show you necessarily where it's going to touch. So here I can see I've got a slope of 3. Okay, here this is 3, this is 2, 4. So it means I'm going to have to go up to, right, to -2, 4 that is. So I'm going to go to -1, 7, 0, 10. So 3x plus 10. We can confirm this because if we plug in -2 to x, we get 4 for y. So this one is when x is less than -2. The next rule, this is a flat line at 4. So we're going to use 4. And this is a starting and ending point. So here, because I said x is less than -2, here I need to start with greater than or equal to. So see how one has the not equal, the other one has the equal. And then this is a personal choice. I'm going to have it stop at 2. You could have it or equal to 2 as long as you change up the next one accordingly. All right, last one. So where you got to be careful, this has a negative slope. So if we keep this going, the slope, it's going down from left to right. So you're going to have -3x because the line is falling left to right. And if you work your way backwards, so you're at 2, 4, 1, 7, 0, 10. X is greater than or equal to 2. So again, only one of them gets the or equal to. So that if I plug in the number 2, it's clear that you only plug into the bottom rule. If I plug in the number -2, it's clear that you only plug into the middle rule. This stuff is really, really tricky, folks, but I think with a lot of practice, some examples, we can really develop some strong piecewise skills. Before we move on to, again, the absolute value function, which is a special example of a piecewise, and we'll see what that is as we come up. So guys, thanks so much for watching. Again, super tricky stuff, but just keep a positive mindset, keep up the great work, and remember that you can do it. Okay, folks, thanks again for watching. Don't forget to love math. Have a wonderful, wonderful day.